Thanks everyone for coming to this talk. I talked to Nick a little bit about timing earlier and mentioned that my talk is pretty modular. So if there's at any point you have questions or want to discuss more on whatever I'm presenting, I'm happy to stop and sort of like go through the discussion. So there's kind of like no need to like go make it to the end of the talk. The full set of slides are here because I'm preparing for like a speaking qualification thing for PhD. So this talk will cover a bunch of work that I've been doing in the past few years relating to explainable AI in the attempts of answering this question of how to make practical impact with XAI. And the focus of this talk will be about methods and evaluations for what I'm calling diverse users and use cases. So like, please don't hesitate to stop and ask questions or bring up any points that might be relevant to things that you're working on throughout the talk. And I'm not great at looking at the chat. So if anything comes up, Nick, could you just tell me?
Yeah, I got you.
Okay, awesome. All right, so I'm Valerie. I'm a third-year PhD student in the machine learning department at Carnegie Mellon, advised by Amit Talwalkar. But I work with like kind of a bunch of people, and my research interests are broadly centered around human-centered machine learning. So a lot of things relating to interpretability, explainability, and also more broadly human machine learning, decision-making and collaboration, and human-in-the-loop systems. Okay, so I'll kind of speed through the motivation because I think most of us already know this. And so there's an increasing number of ways in which humans interact with AI systems. In this picture, like the human could be replaced with a number of different people who are making various decisions and interacting with a number of different ML models. More concretely, this might mean that models are supporting decision making. So one use case we'll revisit later is the use of machine learning to support fraud analysts to make better decisions in catching transactions which are fraudulent. But more broadly, this decision-making pipeline kind of applies to a number of different real-world settings. In these cases where humans are being supported by models in decision-making, questions of when should you be using the model predictions, here being the fraud score, naturally arises. In other cases, models might be used in algorithmic decision-making. For example, a loan applicant who is denied a loan might want to know how they can improve themselves to get a loan. So in all of these use cases, XAI is well motivated, particularly by the lack of understanding of black box models. And so there's been a number of methods that have been introduced in these various use cases to potentially help humans make better decisions, whatever those decisions may be. And as many of you already know, that the field has grown tremendously over the years. There's a number of methods that have been proposed. And it's kind of crazy how, I mean, just look at the whole community that exists here of how many people are working on these kinds of problems. But with that, what we talk about in this work is sort of the current state of XAI, which is that while given this sort of flurry of method development, researchers are increasingly looking at whether or not these methods which have been developed are actually useful for any real world applications. And I think that makes perfect sense because a lot of these motivations that are written in the introductions of papers do seem to suggest that explanations should be useful. On the other hand, as models are being increasingly deployed in real world settings, there are a number of XAI consumers who also want explanations for their real world use cases. But what we observe here, and this has been talked about in a number of other works as well, is this disconnect between what consumers need and what the potential like explanation methods that are being proposed by researchers. And I think the sort of intuition behind why this gap exists is that researchers propose methods that are often very technical in nature and address some like technical objective that may or may not actually correspond to the real world problems that XAI consumers might have. So in this work, we talk about the way in which we think that the community should be moving forward in terms of bridging researchers and consumers of XAI, which is what we call embracing a diagnostic vision, defining diagnostics as tools which provides insights into model behaviors that are targeted, well-defined, and useful for specific downstream use cases. So as an analogy, consider a doctor, like sort of the way we want to think about a diagnostic is, for example, for a doctor who's trying to understand a patient's health, they have a number of tools at their disposal, for example, x-rays that we know can identify bone fractures, heart rate monitors that could identify irregular rhythms. The takeaway here being that neither tool enables the doctor to broadly understand a person's health, but each can be useful if applied properly to a well-scoped problem. And so we hope that a similarly rigorous approach to establishing connections between methods and use cases is sort of taken up by the XAI community as well. And we talk a bit more at a high level in this work about how we can establish explanations as diagnostics. And one of the most important pieces of this is coming up with like a well-defined use case. So not just saying, oh, I want to increase trust broadly or interpretability broadly. Like, what does that even mean, right? Many of these consumers actually have well-defined use cases and actually a corresponding metric of success that determines like how well they're making a decision. And I think even worse is asking consumers if they just like an explanation, because what does that mean to just like explanations that they're getting, right? And so with that in mind, considering what types of methods may be suitable for this use case that has been defined. Sorry, I'll go back quickly in terms of defining a use case. This often will require talking to real consumers, or at least like getting to know what are like the things people care about. So I'll go into that in more detail later. This is pretty straightforward, identifying either existing methods or designing ones that might be specific to the use case that you care about. And then finally, evaluating this method on the metrics that you defined. And if successful, then you can consider this explanation to be a diagnostic for that use case. And you might be wondering, who are these different XAI consumers? In my sort of recent work, we have looked at a number of different use cases, and in many of these cases, talked to real people who would be consumers in these various settings. And I'll kind of go through that a little bit for the remainder of my talk. And then sort of interesting questions about new methods and evaluations will pop up. But I think it's actually been really fruitful to find these real world use cases for XAI in the sense that we're not just like researchers coming up with methods and motivating like the problems with like kind of no end goal in mind. So I found that to be an extremely valuable experience. And for each of these consumers, I'll talk through kind of the 3 steps that I laid out earlier, like how we defined the use case, what kinds of methods we considered, and how we evaluated for success, and sort of what are like challenges that came up in each of those settings. Okay, so the one that I'll spend the most time on is the one I mentioned earlier, with aiding fraud analysts to detect transactions that are fraudulent. So this is joint work with other folks at CMU, as well as folks at a startup called XAI. This financial company provides, or they're building sort of like ML platforms to support analysts in detecting fraud. And so they work with like a number of like banks and things like that. And the goal here is, so the current status quo is that these analysts will just make decisions on their own, but they've been increasingly piloting settings where the analysts are supported by ML models. And in this study, we actually conducted, well, the goal here is we're not sure whether or not providing explanations might improve the analyst's ability to interact with this ML model, given that the analyst does have a lot of domain knowledge coming into the task. And so if we were just to introduce the model and give them a score, it's not clear whether or not they would just trust the model or follow along. And so here we studied whether or not explanations can help analysts do better at the task. In terms of methods, we evaluated 3 popular explainers. And in each experimental condition gave analysts a different explanation to consider. And the way we presented this is pretty agnostic to how the explanation actually works, in that the analyst has obviously no background in terms of like ML or CS skills, and what they really care about is just understanding, okay, so what kinds of features does this model that I'm interacting with consider to be important? So like a green next to like these top features would be considered, would tell them that like the model views these features as being important, and the red would view it as, or sorry, like positive versus negative. And so basically we turned like the feature importance like values into just these like positive and negative values that are very easy for the analyst to understand. So we ran a user study with real analysts using real data, interacting with the actual, like explaining the actual model. And what we find is ultimately that, and so dollar regret is this like metric that we've defined according to like business goals that the company has, and so lower would be better. What we end up finding is that there's no statistically significant difference between the 3 explainers that we consider. And not only that, none of them outperformed or allowed the analyst to outperform just giving the fraud score alone. So while this was like a real world evaluation, it was a bit disappointing to find that none of the methods that we considered actually ended up helping the analysts do better on the task. So this brings up like, I guess, a meta discussion on like, you know, the limitations of real world evaluations, which is that you know, these studies take a significant amount of time, especially when you're working with like real world experts. They have like, you know, normal day-to-day jobs and are not going to drop all of that just to participate in your study. So they're very generously took time, you know, for like an hour a day to like review transactions that are not actually part of their normal work. And this means that like these studies take a longer time to finish as well, and fewer explanations or methods in general can be evaluated. And the unfortunate thing is, if the results are not meaningful, that's probably difficult to repeat these studies in an extensive manner. And so in this like visual on the right, what we often see is that out of like all explanations that exist in the world, the ones that end up being chosen for the user study might seem a little arbitrary. You know, it might be the most popular ones that people know of, or the ones, and so on. So in more recent work, we talk about ways in
Valerie,
which,
should I
yeah.
interrupt for a question real quick?
Oh, oops, going back. Okay.
Right, yeah, could
How
you
do
go
I
back?
find the chat box? Oh my God.
It's okay.
Oh.
There's no questions, but also I'm
Oh,
not
okay.
in the chat for you. Don't worry.
Okay.
Could you go back another slide?
Yeah.
Sorry, one more. So I was curious, so were these the explanations that you showed, or whoever conducted the experiment, that were shown to the users, like the analysts?
Yeah.
Okay.
So we basically, in terms of like, because this is real world data, there's like a lot of features. And so we don't show like values that are attributed to each feature for all features. And we just take like the top 6
Yeah.
and then make it into like this positive negative thing. So it's
Right.
like easier for them to consume.
I was curious. Yeah, it definitely makes it easier because you're like removing like some sort of information from it. But I was curious, like, how did you come to that decision? Was there like a pilot study or previous research done that shows like you shouldn't show the feature importance values or like the relative relevancies and only show like the top 5 sort?
Yeah, I think this decision certainly wasn't as principled as it could have been. I think the decision was made largely because this explanation was sort of part of a larger interface that the analyst was working with, which I don't show here. And so if we took up a lot, and so basically we just added this like widget to show the explanation, but because everything else like presenting the actual transaction and other information already took a lot of space, we kind of decided on this to like minimize the additional information
I
that's
see.
being
So it would be like information overload if you had, because I was thinking it would be interesting if, you know, maybe the number 1 feature had a really large value and everything else had like a very small negligible, maybe positive or negative correlation.
right.
Right. But yeah, I could see how you'd want to like not overwhelm them.
Yeah, that makes sense. And certainly I think if we had that kind of hypothesis in terms of how to best like support decision makers, then I think we could even do like a smaller type of study before applying this to like a real world setting. But I think that's a great point.
Okay, yeah. Thank
Can I
you.
have a question?
Yeah.
So what would you expect would be the differences between like 2 explanation algorithms? Like here this is Lyman tree shot, but at the end this will look the same, right? Right, like in the right.
Oh, yes. So the difference is which features show up as being in like the top 6 set of features, because I think this data set actually has like hundreds of features. So in theory, like these different explainers could attribute like importances to like different features for the same transaction, and sort of the positive negative attribution could also differ. So the colors would differ, the features would differ.
Yeah, okay, but from the perception standpoint, like the user would observe the same kind of.
Yeah, the user would observe like a similar interface, and I think that's okay. But what I think could matter is, for example, for a given type of transaction, if the user has some domain knowledge about like, oh, which features might be important, and if they see like, oh, maybe the explainer or like the model as viewed through the explanation thinks like, oh, this feature is important versus another one, they might decide to override like the model prediction given like their domain knowledge. That's like one hypothesis for like how analysts could use like the explanation, and it wouldn't really depend on how that was computed. Okay. Are there any questions?
Yes. Yeah, sorry, could I ask one quick?
Yeah.
Sorry, I might have missed it, but were they were experts in the domain? Were they the users or?
Sorry, what do you mean by users?
Like the people being tested, like the
Oh yeah,
human subjects.
So they are like analysts by training.
Okay.
So
they would be like, sorry, so they'd be like domain experts, I suppose.
Yes, basically.
Because I just wonder, like,
so they're not like randos who are trying to learn how to use these explanations on the spot.
Yeah, because I've always kind of felt like when people are domain experts, like explanations don't make much difference, right? Like, because it's something like MNIST, if you were kind of to show people an explanation for something, why something's an 8 or a 6, I wouldn't imagine it would help them much because they know so much about it already. And I just wonder if a similar thing is just happening here, you know, but it's a bit different, but yeah.
Yeah, I think the thing is, like, given their sort of domain knowledge and prior experiences, they probably have learned a lot of like tricks and sort of hacks that like they could probably look at a given transaction and try to have a sense of whether or not it's fraud. But I'm sure there are likely edge cases like for each analyst that maybe they're like less familiar with. And in those cases, you might need to like convince them that, oh, like here's what the model is doing, or like why you might want to like trust the like recommendation that's being given you. So yeah, certainly the reason why this company is even considering like using AI like support is that these analysts certainly aren't perfect. And it's why they're like exploring like even the use of like these automated systems for decisions.
Yeah, no, it's interesting. Yeah, thanks. That's all I wanted to ask.
Okay, yeah, thank you.
Sure.
Yeah, and I think like this sort of experience has been really interesting in that it's not like just giving Turker or like user like crowd worker on Prolific like understanding like the complexities of what it's like to work with real world consumers is certainly different. Okay. But yes, with real world evaluation certainly comes with limitations, as I mentioned. And so in more recent work, we propose the use of simulated evaluations, or SimEvals for short, to augment existing workflows. So before conducting a user study, we propose that SimEvals can be used to screen designs for the user study, which includes which explainers should be presented to the user before running a potentially costly user study. And in this workflow, basically we would train a SimEval for each candidate explainer and sort of use like best performing ones for a user study. A little bit more detail on that. Recall the previous decision-making pipeline. Here we replace the human with a machine learning model. And more specifically, SimEvals involve training algorithmic agents that take as input the same information content, which includes like the explanation that would be presented to a participant in the user study to predict answers to the use case of interest. The workflow for training each SimEval follows like a pretty simple 3-step process. First, the researcher who is training these SimEvals would need to generate data that resembles information that users would see, specifically with ground truth answers. For example, if somebody was interested in this use case of forward simulating a model's prediction on a given point, then there's some additional information that would need to be provided, like the data set, model that's being used, and the explainer that's being considered. And then here we would generate this use case grounded data set where each entry corresponds to the input, which corresponds to like information that would be provided to the user, which include like the data point and the explanation on the point, and then the sort of like ground truth answer, which is the model's prediction on that data point for this particular use case. And then we would, the second step is each agent is trained on its own data set following standard ML procedures. And in the paper, we have more details on how to like encode different types of explanation methods and ablate different kinds of agent architectures, but I won't get into those details here. And then finally, we propose the use of the agent's test accuracy as a measure of the predictiveness of the information that the agent was trained on. So by comparing this test set accuracy, we can identify, which explanations might be promising for a user study. So let's make this more concrete. In the paper, we instantiated SimEvals for 3 different use cases: forward simulation, counterfactual reasoning, and data debugging. Each of these use cases are motivated by prior work listed here, but also likely a number of other papers. And the goal was to see whether or not SimEvals can be useful in an evaluation workflow. So we compare like SimEval accuracies to findings from user studies. And this involved comparing to prior work, like user studies from prior work and their results, as well as running our own studies on Mechanical Turk. So for each of these use cases, we considered a number of explanations and baselines, and we compare like the test accuracy between what SimEval gets as well as what the human gets, and on sort of like the same types of questions sampled from like the same data set. And what we find is that humans perform better on explanations that SimEval selects as promising. But as evidenced by these differences between the raw accuracies of what SimEvals and humans get, we emphasize that these accuracies cannot be interpreted directly as the explanation's utility to a human. But these results show that SimEvals should, so showing that like you can't just replace ML models with running like user studies altogether, but rather like this algorithmic approach can be used to select more promising explanations. And these sort of, you might say, yeah, these use cases aren't like, the most realistic. So let's go back to the fraud detection one and see whether or not we can get similar results by considering running this algorithmic evaluation pipeline on the same data that was looked at by the fraud analysts in the user study that I talked about previously. And what we find here is that using the SimEval evaluation approach, there's no statistical difference between the explainers. And this very closely matched what we found in the user study. And what's interesting about this is the user study took probably 6 to 9 months to get this seemingly negative result. And we were able to like run this algorithmic evaluation in a matter of like weeks. And this was done by my master's student who even needed to get like set up with like the system. So the takeaway here being that if we had run this evaluation before we started the user study, maybe we could have tried other explainers or other, instead of like considering these same 3 that we did in the user study. Share the on time. Okay. So that sort of wraps up this first use case, which I had intended to spend the most time on. The second consumer that we have worked with are scientists, and more specifically, folks who work in comp bio, computational biology. And here they have a very different use case for why they're interested in XAI. The reason why comp bio people are training, or the reason why they care about XAI is that they're more and more training predictive ML models on large amounts of biological data. And these models are not only being used to like make predictions with like high accuracy, but what they care about is using these models to identify new or hypotheses of how like different biological mechanisms can work. And note that these are like hypotheses of what might exist because they will need to be like validated in like real like lab experiments down the line. Because by no means does something that a model, what an ML model suggests, like what actually happens in real life. So just like consider, for example, you might have a model trained on like DNA sequences, and what they care about learning is or identifying are new binding motifs for different transcription factors. And the way that what we've seen in prior work has done to identify new hypotheses is looking at clusters of these sequences that have like high importance as attributed to by like different explanation methods. And as I mentioned earlier, in terms of actual evaluation, these hypotheses need to be verified in actual lab settings. And so there's sort of like a similar parallel here with what I mentioned earlier, is that like actually verifying whether or not the explanation helped you come up with like good hypotheses is kind of an extensive process in that you don't get like, either you need to run a user study or you need to like run real world experiments, like lab experiments. And so those kind of like don't come for free, and you can't just try a bunch of different explanations. So what we propose here is similarly the use of synthetic data to help identify potential limitations of explanations before kind of going to like new data that you want to like identify like new biological mechanisms from. And so we introduced this idea of like coming up with synthetic inputs, for example, inserting transcription factor binding sites into like sequences, like where we like know which one should be like the ground truth, or like where the like correct locations are, and then running like sort of this explanation to hypothesis pipeline through and seeing like where we actually get like the high feature importances versus what we expect, as a way to see whether or not like this explanation might be useful. And we kind of like show how to do this for a number of different like real world applications that compile people care about. Unfortunately, I don't know the most about compile, and so it was obviously thanks to like our collaborators who helped a lot with making sure these actually make some sense. But the point here is that in many cases, there's not a lot of use of like synthetic evaluations in like the comp bio literature. And so in this work, we kind of like highlight the potential like importance of that in sort of like a similar vein to like the SimEvals that I mentioned earlier. Yeah. So that was just
so
yeah.
Can you like go to the previous slide?
Yeah.
So I always have like hard problem with this. If you want to evaluate explanation against the ground truth, which you mean like this ground truth is in data, right? So how do you know
we construct it as such, yeah. But
so
in practice, you wouldn't actually know.
Yeah, okay, but how do you know that the model actually learns what you want it to learn, right? So how do you know that the explanation is wrong, or this is actually how the model thinks, but this is just the result that you don't like?
Yeah, so this is, and we don't propose any new methods here. We actually borrow from like existing work in the XAI literature, and later I could probably send you some of the specific like methodology that we borrow from and basically like apply to these combined settings. There's like a few different work that does the synthetic evaluation, not for combio settings, but in like the ML literature. And they basically, to my understanding, like train these models. And oftentimes these data sets are pretty synthetic, but like to very high accuracy. So you like, you make sure your data encodes like the rules that you want it to. And so you enforce like the model should be able to learn that. And then
I
like,
agree. Like I agree, and I know that this is apparent in the literature. I just like from my own experience working with such models, they actually learn different stuff, and I think that explanations show what they actually learned. This is just not something that was in data, and yeah, this is why I'm kind of skeptical. But
okay, yeah, I'd love to talk more about that, because like sort of what types of data were you looking at, or like
especially because if you think about it, like data encodes global relationship, right? So maybe global explanations should look in a way that you want it to look. But local explanation can actually be really different. Like this is a local working of the model, especially with deep neural networks, they can do really various stuff. So expecting them to show the ground truth in data might be kind of like, of course, we humans would like the explanation to look this way, but actually in practice it might not. Yeah.
Right. Yeah, that's interesting. So in terms of like the other work that like, and I think a lot of these we design like really simple like rules in the data. So like it's sort of what CombBio people would actually say like potentially too synthetic as a way to ensure like the model only like learns those rules. But I could imagine like if you have more complexity in the data, like then there's like high chance that it doesn't really learn what you want it to learn. But yeah.
Actually, one cool idea is to like produce an interpretable model and then treat it as a black box and kind of infer local explanations from the interpretability.
Yeah, so like example C here is one that we tested on what they call like a biologically informed model, which the way they get their explanations is looking at like the weights of the model, and these different edges of the model are constructed in a way to replicate like different pathways that are sort of like known in science. But even with those types of approaches, by using our like synthetic evaluations, we still find that like the pathways that we expect to be important, like by construction in the data, like aren't necessarily attributed the right importances by looking at the weights. But yeah, I totally agree with the concern on the local explanations here. I'll think more about that. Okay. So yeah, that was ongoing work with CombBio people. Another, I think I will just go through one more use case, and this should be short as well. We'll skip the last one because there's not actually a real user there. The last one is a theory work. Okay, so yet another real world use case that we have been working on is for improving the conference peer review matching process. We worked with Nihar Shah, who I would say is probably one of the experts in conference peer review. And if any of you have ever been a reviewer in a conference, you probably know that the paper that you've been assigned to review or have complained about like the quality of paper review assignments. And this is because that given like the increasingly growing size of conferences, many of these paper review matching processes are done using large language models. And so not actually with some human going through and being like, hey, here's who I think you would be the best reviewer for this paper. So it's done by computing similarity scores between the paper and candidate reviewers. But what we're exploring here is potentially the use of explanations or additional informations to help conference organizers like ACs or PCs potentially going through and revising assignments to improve like the matching process. And note that like this is a slightly different use case in the sense that with enough time and efforts in the world, probably somebody without any model support or any explanation could do a really good job. But the goal here is like, how do you allow them to do similarly well, but by like in a faster manner.
Hey, Valerie.
Yeah. Oh, I see your comment.
Yeah, go ahead.
Yeah, so I think the bidding comes before this is done. So I kind of abstracted away like this process. I think the bidding is kind of factored into here, but for the most part, a lot of what you and I think I can check with Nihar, but I think my understanding is that there's like a similarity score. It's not just computed based on like the actual text between like the reviewer and the paper, but there's also a few other like factors into this like optimization process, which include your bids and some other aspects like how senior or junior people are, things like that. But yeah, but broadly speaking, a big component that determines this is this like similarity as determined by the language model. Okay. Yep, no problem. Yeah, so after all of this is done, what we would ideally like to do is to be able to go through and identify some of the bad assignments. And yeah, anyways, there's been some other surveys on like the peer review process and like all the problems with it, which include assignments. So this is another setting where like real world evaluation is pretty difficult. And so the way in which we're looking at first tackling it is through constructing a proxy task. So instead of conference organizers, can we use like crowd workers, but have them do a similar task that kind of mimics the task that like an AC would have to do with like revising paper review or matching. But of course, like we are looking at down the line, porting this back to like the real world setting. So the example of this proxy task that we designed looks a little bit like, having a query summary. So think of this as the paper that needs to be reviewed, or like the abstract of the paper that needs to be reviewed. And then you have like 3 different articles that you would like to match this summary to, and a score corresponding to each article. And you can think of the article as being a potential like candidate reviewer. And so you're picking from a number of reviewers, and the reviewers have like a bunch of papers that they've written in the past that might be like matched to the candidate paper. And it's not always the case, of course, that the highest scoring article or reviewer based on like this language model plus other stuff score actually corresponds to like being the best match. If that were the case, then our problem is solved. So first we looked at applying post hoc explainers to look at what what tokens were important for the scores, with blue being like these were negative and red being like words or phrases that were positive. And what we find is that these highlights don't make a whole lot of sense. And if the goal is to help somebody do this task better or faster, this certainly would not be the way. And so I won't go into detail here, especially given the time, but develop a use case specific method that looks at sentence level similarities and comes up with highlights that way for like each of the candidate articles with like the summary text. And what we find in at least the proxy task is that for difficult questions shown in red, our method does better than both the control setting where there's no additional highlights that are shown to the user, but specifically finding that like black box explainers don't necessarily work. In fact, they make people worse on these difficult questions. And by difficult, we categorize that as being questions where you can't just look at the score and use that as like the highest scoring one is not actually the best answer. Yeah, so I guess the main takeaway here is that in certain use cases, you can't just apply things out of the box and need to use more information about what you know relating to the task to design better ways to help like the users make better decisions. I know we're coming up at 2 o'clock, so I'm going to skip this, but just run through really quickly some of the takeaways and lessons learned from looking at these like various use cases and talking to like real consumers. The first being that there is like much this diversity of use cases and users. So I think it would be unrealistic to expect that, you know, any old method that, while maybe well known, should work well for every user and use case. And so relatedly, real world evaluations are costly. So thinking about how to do better simulated evaluations or synthetic evaluations would be really fruitful to save time on like real user studies or experiments. And then finally, what I was mentioning earlier is that like oftentimes we find that existing methods don't work. And so you probably we need as a community need to think more about what are use case specific methods that can be more effective, but obviously don't have all the answers there. Yeah, thank you all so much for listening. This certainly would not have been possible without my collaborators. Yeah, and let's stay connected. And yeah, thank you all for the questions already.